Hi guys, welcome to this quick recording concerning two items. First of all, one that is from last Thursday when we were doing the magnetic field produced by an infinite wire. Carrying a current, of course. Uh, I made a mistake in the class because of the fact that when I was busy with the cross product, uh, I did not really handle the cross product in the beginning, right? So I ended up looking at one of your books, and one of you guys' books who was in there, and we corrected it. And we corrected it by going back to the fundamentals, and basically this is just a reminder of how it went. So basically, we go back into expressing the. I'm gonna post this thing on Canvas later on today. So ds, the element of the current, is on the x-axis. So it's dx, the length of which is dx, I hat. And the vector r hat points in this direction, which is given by the angle theta, except that it has an x component which is negative, and a y component that is positive because it's pointing in the other direction. Because it's a unit vector, length must be equal to 1. And its x and y components are negative sine theta and cosine theta, and you can easily convince yourself of that by looking at the projections of this whole vector r over its length. And its length is just square root of x squared plus y squared. So that's basically part of the approach that we ended up doing. So we formed the matrix, the determinant of this matrix. That's how we find the cross product using the x and yz components of the vectors in question. And the vectors in question are the vectors ds and r hat. R hat has a length of 1 and its components are negative sine theta, cosine theta. ds has a length of dx in the I hat direction. So there are 0 components in the other direction. Just by following the rules of the determinant, you can find the value as being expressed as the cosine times the dx in the k hat direction. And that's basically what we ended up with. And we integrated, and you do cosine. Basically, you change from x to theta by noting that tan theta is equal to x over y, the opposite over the adjacent. And from there, basically, you do the dx in terms of d theta. You pick up a secant squared, and there is a secant squared from the r squared. Remember, r squared is x squared plus y squared. And secant squared cancels secant squared. At the end of the day, you will be left with cosine theta d theta integrated between negative pi over 2 to pi over 2, and we got the result that is a famous result. Anyway, so that was one thing. We could have gone a different route, and I think that's the approach that the book took. Again, you go back to the fundamentals of the cross product using the right-hand rule. But in this case, the cross product, there is actually a sign of the angle between them. And the angle between the ds and the vector r is this angle, which is 90 degrees plus theta. So 90 degrees plus theta, and you use the identity of sine of the sum of two angles is sine of the first, cosine of the second. The cosine of the second is cosine of 90, so it won't happen. So the only thing that's going to remain is sine of 90 degrees plus theta is cosine theta, and the answer is going to be identical to the rest. And it's in the k hat direction because the x is in the plane, the y is in the plane, and the z must be perpendicular to them, basically, following the right-hand rule. So that's basically the argument, and the answer after that just follows straight after that. So basically the integration and everything else are identical. So that's one item. Item 2 was problem 38 that we did actually from chapter 29. And we just basically, the question was to find the first derivative and the second derivative and make sure that the function actually evaluated at the center between the coils, not at the origin. So you have to remember, you have an n coils on one side, n coils on the other side, and they have both radii, they are symmetrical, they have the same radius r, and the separation between them is r. So that is the condition that we are working with. This is how Helmholtz coils work. So they have radius r, and the separation between them is also r. Smack in between, you were supposed to find the derivative, the first derivative and the second derivative, and ensure that this derivative is 0. And we did that. And I made a claim in class that actually the third derivative also vanishes too if you were to calculate it. We didn't calculate, it's a very long calculation, but if you were to do it. So the first term in the Taylor expansion should be the fourth derivative, which means that this function is going to be the constant plus 0 times x plus 0 times x squared plus 0 times x cubed, and the first correction is going to be of the x to the power 4. Remember, when you do the Taylor expansion, you're dividing by n, 1 over n factorial. By the time you reach the fourth derivative, you're dividing by 1 over 4 factorial, which is 1 over 24. So whatever that coefficient in the Taylor expansion is going to be divided by 24. So the correction is going to be small. So the function is going to be mainly constant. And I made a claim also that this thing is going to be all the odd derivatives. So if I were to go to the fifth derivative after I survive the fourth, the fifth also is going to be 0. So it's actually the next correction after that is going to be the sixth derivative. So this is really looking as a constant function, at least in that range. So after we juggle this expression, remember, first of all, it was not expressed as such. I don't have the book with me right now, but it has an r squared plus x squared in this case. And in here it has 2r squared plus an x squared minus 2rx. And one of you guys asked that the form initially did not look as such. When we expanded the square in here, it gave us the correct value. But what I'm doing in here, I pulled the r squared actually out and defined a new variable, which is y over x over r as being y. So in a sense, this is in terms of a dimensionless number y. So this whole thing then carries all the dimensions of the magnetic field and the number of turns in the coils. Mu naught is the permeability of the medium. Y is the current, and 2r is the r is the radius of the coils, or the separation between them is the same number. So all of this thing becomes dimensionless in terms of y. We're going to do another change of variable. Actually, we're going to shift from the starting point as being one of the coils to the starting point being smack in the middle, and we will see the symmetry right out. Okay, so when we do that shift, basically we, instead of staying at x equals to 0, we're going to go at x equal r over 2, which means y equals to 1/2. So we shift everything to 1/2, and I call the big X at this point temporarily, okay? Big X. Then when we shift the new variable x is going to be y minus 1/2, which means that y is going to be x plus 1/2. When you do the substitution in here, by subbing y squared and 2y in here, and doing the algebra, I get this function in here in terms of the big X. But for notation purposes, I'm writing lowercase x, and you will see why. Because I'm going to plot this function on GeoGebra, and GeoGebra doesn't like capital X or any other variable other than x. So the big X now became small x. Has nothing to do with the original x. The original x is measured in meters. This one is a dimensionless number. Has no it's in measures of r. Okay. So then the function that I'm supposed to plot is b over this coefficient, which I just called it b naught for convenience, so that I have a dimensionless, true dimensionless function to plot with, to play with. And in here, I'm going to pull up a 5 over 4, which you get from that shift in origin, plus x squared plus x to the power negative 3/2, because of the fact that it wasn't the denominator. So when you pull it up, it becomes a negative 3/2. Plus the second term will be similar, except that plus x squared minus x at the end, to the power negative 3/2. Again, just follow the algebra, you're going to get there. Here is the point though. This function is an even function in x. This term by itself is not even or odd. It has no parity whatsoever. Because if you switch x, this new expression changes completely. This term by itself also is not even or odd. It has no parity. But the combination of both of them is even function, because when I change from x to negative x, this won't change, but the positive x becomes a negative x. So I have the second term first, and this negative x becomes a positive x. The first term shifts, so they shift places, and the plus sign stays the same. So the function itself is actually an even function in terms of x. That's what I was arguing earlier, that all of the odd terms in the Taylor expansion will vanish. So the only terms that are going to remain are the even terms, and the second derivative is 0. But the rest may or may not be 0. Okay? You know what? I didn't do the sixth derivative. I have a feeling that also that's going to be 0. So probably only the fourth, every over fourth term probably will pop up. I'm just throwing this idea out there. I have no idea actually. I need to, and you will see even on a computer it struggles to get into derivatives. Anyway, so when you plot the function, and let me show you the reason why I put this one actually in LaTeX. And if you guys want the LaTeX version, I can give you the LaTeX version. I'm gonna post just the PDF for right now. This is the function basically as I define it. It's the same function, and I had difficulty with the LaTeX because LaTeX is really not that great in terms of graphic functions. Because I can't just do the power -3/2. It was giving me an error, compiler error, big error down there. So I had to use 1 over square root of this thing cubed plus square root of this one thing cubed. That's the function I'm plotting. Of course, x times x is x squared plus x, and x plus times x is x squared minus x. So there is a kind of weird thing in here. The function, of course, we plotted from -1/2 to +1/2. That's where the coils are. That's what the magnetic field is. That's what we want. So if we're going to do an experiment, for example, to throw a beam of electrons between the coils, we want to trap them in that region, and we will see the coil. And that's part of a lab actually. That is here in this college is done in physics 204. I'm sorry, the third sequence of the calc basis. In the other campus, our sister campus, actually they do it in physics 2, where you guys are at. So it's the ratio of E over M. And there is justification for one in being in here and justification for the other one being in there. Not both are valid, okay? So there is no critique for that. Anyway, so the ratio of the charge of the electron over the mass of the electron is done based on this. So you throw a beam of electrons, you accelerate them into a region where the magnetic field, you want it to be as constant as possible. That's the advantage of these coils. So once you do that, then you form that ring, you measure the radius of the ring. Based on that, you can find the ratio of the charge over the mass of the electron. So again, that's why the domain of this function between the minimum value is -0.5 and the maximum value is 0.5. The y max is up to 2 because the function is actually around 1.4. It hovers around that. Of course, we're dealing 1.4 times this number B naught. So B naught is determined by the number of coils, the permeability of the medium, the current, and the size of the coils. So there is a number for the magnetic field. It's going to be in Tesla something. Anyway, so the magnetic field is almost constant, of course, in this region, which is equal to some constant, where you just sub in x equals to 0 in this expression, and you get this number 1.343 times B naught. B naught is the scaling factor that I pulled earlier. And this is a famous expression for the magnetic field. If you were doing this lab and you were measuring the current I, and you were given the number of coils, then you can, and the radius of the coils, then you can find the magnetic field, its value. As you change the voltage, the current changes, and as the current changes, the magnetic field changes. You measure the radius little r, not big R. Big R is fixed for the coils. You measure the radius r, you have the current, and you do a little bit of algebra, and then you find E over M, the ratio of the charge over the mass. So that's you need to calculate the magnetic field using the expression that you have for I, for the current from the ammeter. Just to argue that this is basically constant, if I go to the edges, you probably see, let me try to zoom in on this function here, you will see that it drops a little bit to the edge, and here there is a drop. I mean, it's not really constant. And that's because, as I was saying earlier, there is a in the Taylor expansion, the fourth term starts to appear. Okay, but the first, second, the first, of course, is constant. The first derivative, the second derivative, and the third derivative, all of them vanish. As if you want the magnetic field at the edge, that's really right where it gets the smallest possible. It drops from 1.43 times B naught to 1.35 B naught, drop of about 5%. Let me share with you GeoGebra just to show you how this thing look like. Again, I am plotting the function in here. I know. Let me try to move this one in here. So I'm plotting the function in here. It's the same function that we've been dealing with all along. 5 over 5, so it's the same even function. We shifted the origin. So this x equals to 0 on the graph is actually the middle of the coils. On one side there is n coils, and on the other side there is the other n coils. Okay, so smack in the middle is the point of where we're measuring the magnetic field. But this is a function between x negative 1/2 and x less than half. Okay, and if I find the value of f naught 1.43, and if I find the value of f 0.5, and it's going to be the same value whether you go positive or negative, it's 1.35, and that's where I got a discrepancy of about 5%, basically shift between the two values. If I were to find the first derivative, I'm not going to bother you with a calculation. I mean, I know we did it in class actually, and the first derivative, at least GeoGebra is not really suited for this stuff, for doing symbolic manipulations. Probably Mathematica or something else would be better. But at least it gives you the first derivative, and it's a very long expression, by the way. It took a little bit of time, delay, but it gave me the value, not too far. So I have the derivative of the function f with respect to x, and evaluated the derivative at the x equal to 0, for x equals to 0, for the middle. In the class, we didn't shift the origin. We left it at x, at one of the coils, but you sub the value of then x, that x, which is r over 2, and you're going to find the first derivative to be 0. No hard. It's not really hard to do it manually. The second derivative also, I think we did that also in class, and that is actually going to be 0 too. Here, GeoGebra really struggles. I cannot even have an end to this one. I can go as far as I can go here. It's still writing stuff because square root and negative this and that. And it's not reducing the expression. It's just basically plugging in all of the things, doing term by term. And that's why it's really not suitable for this kind of operations. I mean, it's not going to make a mistake if it's a relatively speaking easy function. But if it's, this is a relatively speaking easy function, honestly. This is not a function that is that complicated. I mean, it's just power laws. Okay, granted you have that 3 over half. Anyway, so the second derivative is done in here, which is the derivative of the g, not the original function f. So the derivative of g, and then evaluated as 0 also gave me 0. That's what I expected. And then I actually went a step further, and this took a long time, honestly. So I thought my computer froze. So I asked it to find the derivative of this derivative of the derivative. So this is the third derivative of with respect to x, and also it gave me this even worse expression than the other two. But at the end, evaluated this function at 0, and it gave me 0. And it's predicted to be 0. I didn't do the fourth derivative, but of course you could do it using GeoGebra if you have a lot of time. So if you're going to do GeoGebra, or any other symbolic calculator, you can do it and wait for it. Give it time, okay? I'm going to give you a number. And if you want to find the value at 0, which is the term that is needed for the Taylor expansion, you also have to put that function and send the argument as 0 and wait for the answer. It's not going to be 0 for the fourth term. Of course, it can't be 0. I mean, some terms must survive this Taylor thing, okay? Anyway, so I thought I'd share with you this point in here. Okay. To be honest with you, doing it manually is easier than the computer. So it looks daunting on a computer because, especially GeoGebra is really, like I said, it's not the best suited function for these things. But it does the trick. Let me show you the functions one by one. Hopefully it won't take long. Let me show you this function first of all. This is the first derivative, the derivative of f with respect to x. Again, it passes by the origin, and that's the key in here. I am interested in finding how much it is at x equals to 0, because that's what goes in the Taylor expansion. I don't care about the other sides. Let's go into the h, which is the second derivative, and it's taking a little bit of time to draw it. But again, it's a function that vanishes at x equals to 0. Okay, let's do the third function, the last function. I don't know what color it is. Probably it's not even a, it's kind of a, it's taking some time to plot it. And remember, this range is, all of this function is divided from negative 1/2 to positive 1/2, because that's where the coils are situated, between negative r over 2 and positive r over 2 when we shift the origin there. Anyway, so this is the that function, it peaks somewhere, who cares, and it goes minimum. The point is, it also vanishes at x equals to 0. All of these functions vanish at equals to 0, x equals to 0. Let me see if I can get GeoGebra to redraw. It can't. It's taking... See, I'm trying to rescale the y-axis, and it's not even responding to me. There's so many points to plot. And, okay, I don't care about this one in here. Let me minimize it. The point also is that if I were doing it in GeoGebra, in LaTeX, I have a control over how many points. So for right now, I'm sampling about 100 points for this function. So if I were to do the first derivative, that's another 100. The second derivative, that's another 100, 300 so far. Actually, it's better probably to plot it on LaTeX in this case, but you have to find the expressions. And LaTeX is not really that suitable in terms of writing complicated functions. So once we find the derivatives, we could plot each and every one of them on LaTeX. It should plot them a lot faster, but it won't do the calculations for you. So things are different. Each and every program does its thing. Okay, did it reduce? It did, because earlier this function was not even seen in the horizon. Let me see if I can reduce it further. I want to see where it maxes, that's all. It's symmetrical function also. So with respect to the origin. Remember, the origin has been shifted now, okay? So the reason why it's taking a long time, and it took a long time just to rescale the first time around, the y-axis, is because it's redrawing all of those points, okay? It's trying to find where they are. And I don't know if there is a way of controlling this on GeoGebra. Tell it to not draw as many. Like, instead of drawing probably 1,000 points per graph, let's reduce them to like 100. There's going to be plenty for doing connections. Anyway, so it maxes a little over around 7, or slightly probably less than 7, okay? But who cares about the maximum? All I care about is the values of the first derivative, the second derivative, and the third derivative at x equals to 0. And they're all 0, okay? As demonstrated in there, and graphically also they are all passing by the origin. So it's a very important tool for basically having conditions where the magnetic field is constant, because the last thing you would want to do is have a changing variable magnetic field depending on the position, and then you have no idea. Then the physics will not be yielding. So again, to measure the value of E of m, so basically what you do, you have a gun that shoots electrons using the potential difference. Remember, 1/2 of mv squared is equal to the charge times the potential difference. Usually that potential difference is anywhere between 100 to probably 300 or 400 volts. So it's tremendous voltage. So now we're not talking about 3-volt battery or something. And then you need high enough currents running through the coils to have strong magnetic fields, because that magnetic field is also proportional to the current. So there's those currents of the order of a few amperes, so they are not small currents at all. And then you have to have a high number of coils, hoping it doesn't heat up the system. And what they do is they have them in a kind of a vacuum chamber. They throw in a gas, I forgot what it was, I think it's a neon or something like that. And as the particles come in at that speed, because of the force, Lorentz force, F equals to QV cross B, they come at a 90-degree angle with respect to the magnetic field. Remember, the magnetic field extends from the center of the coils. It goes, it's along the axis of symmetry of the coils. So if you're going to send the beams, you're going to send it perpendicular. Then in this case, they will go in a big circular path because of the cyclotron property of this motion. So that we saw. That's part of chapter 28. Now, how big is the radius depends on the strength of the magnetic field and how fast these particles move in. Okay? So you measure the radius, and there is like kind of a visual, it gives you a visual where you see the beginning of the big sphere that forms, which is a big circle that forms for your projection, of course, one end to the other end, and you measure the distance, which is with a ruler basically. So there is a ruler in the background. You look at the beginning, it started here, it ends there, This is the diameter, divide by 2, you have the radius. You have R, you have I for finding B using that expression that I showed earlier. And you have the voltage to find basically the connection between it and the velocity squared of these particles. And now all of a sudden you have an expression at the end of the day, the only thing that remains is E over M. So in the context of this class, if we were to do this lab, it has to do, of course, using the properties of the magnetic field in a coil to determine something useful, which is the ratio of E over M. In the context of physics 204, it's trying to find one of the earliest elementary particles, namely the electron and its properties. You find the ratio of E over M using this technique. And you find the charge of that elementary particle using the experiment of Millikan, basically where you have droplets that have been charged and they're falling, and due to friction and gravity and the electrostatic field, they balance. So now you determine their charge. So you have E on one side, and you have E over M over the other side, so you can determine the mass of that particle, M. Isn't this amazing? Anyway, so I just wanted to share with you these 2 points, and hope if you guys have any questions, please don't hesitate to send them. Thank you. Where is the stop?